where basically you decide to write, instead of psi, you take the exponential of psi, rescaled with the proper viscosity dependence. And this way, you obtain a linear equation for this new variable, theta. Okay, so now you have a linear equation, which is nothing but the heat equation with some multiplicative noise. Or if you want, you can think about it as a Schrödinger equation at imaginary time. Okay. Schrödinger equation, you will have I in front of dt. And because of that, so because the problem is becoming linear, then it's becoming integrable. So we can construct explicitly the solutions. So now, the short history about Burgers equation. So the Burgers equation was introduced by Burgers in the late 30s. And basically, Burgers was really a mechanical engineer. So what he was willing to do is to find a model for actual Navier-Stokes. And basically, the main motivation is that the Burgers equation was having exactly the same kind of hydrodynamic nonlinearity, the U grad U term, as Navier-Stokes. And because of that, the same invariances than the Navier-Stokes or Euler equations. So then, at the beginning of the 50s, so Cole and Hope showed that it's integrable. They proposed this transform, etc. And basically, since it's integrable, there is something which really lacks compared to Navier-Stokes, is that Burgers equation is not chaotic. And this makes a big difference with Navier-Stokes, and a big difference on which I will come back tomorrow. So then, still, this equation was used as a prototype for nonlinear hyperbolic conservation law. So it's the simplest way you can write a conservation law by putting some nonlinear flux, which is U square here. And basically, this was used a lot by people like Peter Lax, who developed a lot of mathematical understanding of all these problems of hyperbolic conservation laws with the idea of applying them to compressible flows. Okay. And so Lax was a mathematician who was doing both theorems on well-posedness and uniqueness, etc., and developing numerical methods, mainly finite volumes. And so now, basically this was the face of the Burgers equations. But in the 80s, the Burgers equation reappeared more from the statistical physics viewpoint, and also in astrophysics, under its random form or its multidimensional form. Okay, and so there was a regain of interest. And finally, at the end of the 90s, a bit motivated by the fact that still it was applied to some statistical physics problem. Now the Burgers equation is become a kind of benchmark on which you can test some closures that you want to apply to Navier-Stokes. So you test them first in Burgers. Since in Burgers you have exact results, you can assess whether it's true or wrong. And so basically closures, numerical methods also. Many numerical methods are first tested in Burgers, or mathematical construction of invariant measures. So this I will talk a bit about this construction of invariant measures. So now, so just some words about the Burgers equation in statistical physics. So the first thing is that there is an equation that many of you should know as KPZ, Kadar-Parisi-Zhang model for interface growth. So this KPZ equation, which is written here, you see it's exactly the same equation as the Hamilton-Jacobi equation that we have for the velocity potential, except that here now in the KPZ model, what we are considering is a noise in the right-hand side, which is delta correlated in both space and time. So it makes things a bit different from the usual problem of turbulence, where instead of making something delta correlated in space, you want to look at forcing which acts only at large case. Okay, so this makes the thing a bit different, but still there are many stuff in common with KPZ. So then the Hopf-Kohl transform, which is leading to this equation, is actually the equation that also intervened for directed polymers in random media, and in particular, it will be this equation will be the equation for the partition function of an elastic string, which is directed in some direction. So now t is no more time, but it's the direction along which your polymer is preferentially aligned, And basically what you look is is a distribution of the conformation of this polymer in a random potential. So I mean, here I have sketched the random potential as green places where the polymer is willing to be, and the red places where the potential is too high, or the polymer is not willing to be. And you see that you can construct different the full measure of the conformation of the polymer, fixing, for instance, the two endpoints of this polymer. And now, if you look at the partition function of this thing, you get that where typically the viscosity is playing the same role as temperature in this thing. And then, so there are many models for traffic flows, which are also using Burgers equation as a simple problem of compressible fluid dynamics. Okay, so it's intervening in many models for vehicular traffic. So now, on the other side, there is the cosmological aspect of the Burgers equation, which relates to the dynamics of the large-scale structures of the universe. So right after, so a few time after the Big Bang, so there is decoupling of matter between baryons and photons, and after that, basically the main so the large scales of the universe are following this Vlasov-Poisson kinetics. So basically, this is the equation for the distribution function of mass in position velocity. Okay, and so you write this conservation of mass in position velocity, and basically, so here this is just to tell you that the momentum is driving the position, and here this is the force, and the force that you apply is just the Poisson, is just the gravitational force, which comes from the Poisson equation that you integrate otherwise. Okay, so this is called the Vlasov-Poisson kinetics. So in the 70s, Zeldovich showed that the initial fluctuations that you have to put in this equation are actually such that your velocity field to leading order is monovalued. So as if instead of having a full distribution over momentum, you have only one value at each point of space. So this is the leading order things, and also that is potential as we want it to be in Burgers equation. And this led to what is called the adhesion model for the large-scale structure of the universe. So I'm sorry, you don't see much here. So here, what I'm comparing is an observation of the large-scale structures. So it's the things which are, so these are clusters of galaxies. So it's a very, very large case. And this is to compare to the solution to the Burgers equation that we get. So basically, we don't see much, but actually we have clusters, we have walls, and which are resembling these clusters and walls that we have here. So the Burgers equations, I mean, since the 90s, is now used in order to describe, at least at first order, the distribution of matter at large scales in the universe. So this is the cosmological aspect of Burgers equation. So now what I want also to stress is the fact, so this is already something that I have said at the beginning, is that Burgers equation is also having this sort of benchmark. And as a benchmark, so of course, for scientific computing, in order to test methods for compressible flows, so that's something which is clear. Then in physics, basically, there is one thing which is pretty important, is that in Burgers equation, we can understand exactly the nature of the singularities and how they are affecting the statistical properties of the flow. So as we are willing to do in Navier-Stokes with this multifractal model, which was coming a bit out of the blue. So now here we control everything. So then, of course, it's a good benchmark to test universality of what's happening of the statistics with respect to forcing, to the boundary conditions, to the initial data, etc. And also to test methods from other fields. So basically, for instance, there was attempts to be able to write the dissipative anomaly in Navier-Stokes in terms of field theory and of operator product expansion. So this is work which was mainly done by Polyakov. And the first thing that he tried to do is to test it in Burgers equation. And he found out that there was some trouble in Burgers equation. So then you see, you know what to say somehow in that case. So then from a mathematical viewpoint, so I told you that in Burgers equation, we can explicitly construct the statistical steady state invariant measures, but also it's used as a prototype for random Lagrangian systems, so through the stochastic Hamilton-Jacobi equation. And also it has some connection with what is called the weak CAM theory, so the weak Kolmogorov-Moser theory, which is how so Kolmogorov-Moser theory is how the phase space of a dynamical system is changed when you change the parameters. So it's equation of continuity of differentiability of the phase space as a function of your parameters. And weak means that you can treat these kind of things with random forcing, so which means it's an extension of the usual CAM theory. And of course, Burgers' equation is still valid in some asymptotics, so to describe some actual physical phenomena. So of course, in compressible turbulence, in inelastic granular gases, or in the propagation of random nonlinear waves. Okay, so that's these are the applications of Burgers. So Burgers is not just a toy model. It's also it has also some applications.
So
yes.
I mean, so without drive, it's an integrable model. Is that right? Without drive.
No,
without
even with
noise.
Drive. Yes, even with noise.
Even with drive.
Yes.
I mean, you can map it too, but it's sort of a multiplicative noise. So
it's multiplicative noise, but I will show you how you construct the solutions. Yes. So so let's think about let's start to look at Burgers' equation. So what is Burgers? So let's start with the unforced case. So let's put force to 0. So what you get here? So we want to understand what is the effect of this viscosity on the way the solutions are behaving. So if we put abruptly viscosity to 0, and so you get this equation. So what this equation means? This equation just means that the velocity of fluid particles is conserved as a function of time. So you pick a particle, it has a velocity u, and this u is just conserved. Okay. So along the tracers, along the characteristics of the flow, which are solution to this ordinary differential equation. So now this, if the velocity is constant, you can integrate it this way. Okay, so you have that the position of your tracer at time t is its initial position plus t times its initial velocity. So it's just a ray, so it's just moving ballistically. And of course, the velocity then at the particle position at time t is the initial velocity which has been transported. So this is the equation for characteristics. The problem that you see here, so here I've just sketched what's happening. So you start at time 0, different x0. They all have different velocities. They follow this ballistic motion, so they move along these rays. And at some point, some rays are crossing. And the question is to understand what's happening after the crossing of these rays. Okay, the crossing of these trajectories. So how to deal with it? So we need to put some viscosity, finite, and to make it going to 0 in order to understand how to construct properly the equation. So we do the Hopf-Kohl transformation. And in the absence of forcing, this is just leading to the heat equation. Okay. So now the heat equation, you can integrate it. So you can integrate it, for instance, using Feynman-Kac formula. And what you write is that this theta field at position x at time t is an average of some initial potential computed at a location which is a Brownian motion. Okay, so this is just the Feynman-Kac interpretation of this PD. Okay, so so this is nothing but theta 0. Huh? This is just theta 0. Okay, so I'm just saying that theta is the same as what I was doing for the passive scalar yesterday. So what I'm doing now is that I'm writing theta of x as an average of theta zeros along different random trajectories. Yesterday, I had advection in addition to that. So now I don't have advection, so I have only diffusion. So basically, I'm doing an average with respect to the d-dimensional Brownian motion. Okay, with the final condition that so I'm sorry, I wrote it the other way. So with the yes, I'm sorry, t. Okay, so it's t is minus t. Okay, so this is the d-dimensional Brownian motion. This is the initial condition, but it's a backward thing, and the Brownian motion is such that its variance is proportional to nu in that case. okay, in order to get this new here. So let me sketch it. So you want to know the solution at time t. You pick the place where you want to know it. You integrate Brownian motion backward in time, okay, with diffusion nu. Then you have different places where you arrive, where you were at the initial time. You compute the initial value at these places, and you make an average over all this trajectory, and this is giving you the final solution. Okay? So now I'm just rewriting this thing this way. So here I have only W at time t, which is appearing. So I know exactly the distribution of W at time t. It's a Gaussian with variance 2 nu t. Okay. So now and centered on the initial position. So now I rewrite this average with respect to this Brownian motion as an integral weighted with the probability of having my Brownian motion at some place x0. And now I do the average with respect to x0. Okay, so that's fine. This going from there is okay. That's fine. So now, as you see here, I have an integral of an exponential of something with where I can put 1 over nu in factor. So now I want to take the limit of vanishing viscosity, nu to 0. So I just do a saddle point, okay, to this thing. So basically, it's a sum of different exponentials with different strands as a function of nu. So when I make nu to 0, 1 over nu to infinity, I will pick the smallest thing here, so which would be the largest. Maybe I have some trouble. Yes, I forgot that there should be some minus plus here. I'm sorry, there is a sign error in this thing. U2. Yes, there is a minus. Yes, there should be minus. I'm sorry, because from time to time it's U is minus the potential or plus the potential. So here it should be minus, so that you pick, I think, pick the supremium. Okay. Anyway, this formula is right. So the potential at time t at position x is given by the supremium over all initial positions of the argument of this exponential. Okay.
I think that's just a log missing in front of the theta, isn't there?
No, this theta xt is exponential of 1 by 2 nu times psi t, right? The next line.
Yes.
No, next line.
This one, yes.
Yeah,
there is also this here.
Log
yeah, there should be exponential, of course. It's exponential of theta. Yes. No, log.
2 nu log.
2 nu log is this formula. So I should put them. It should be minus 2 nu log. Anyway, so this equal to that is right. So basically what you see is that somehow the way to get the potential at time t is a supremium of the initial potential minus some term which is decreasing if you take further and further distances from x. So if x0 is going further and further from x, this term is decreasing, okay, and might compensate the potential. Okay, so basically there is a balance here between the potential energy and the kinetic energy. Okay, so it's a Lagrangian actually. It's an action. So now, yes.
Need theta to be positive. That's why this is the only solution, right?
I'm sorry.
Theta is a positive.
Yeah, theta is positive. Yeah, so you can, yes, theta is positive. Okay, so now, of course, if you think of this thing as a variational principle, you can write the Euler-Lagrange equation. So basically, you assume that the sup is attained somewhere. You take the derivative of this thing with respect to this position, make this to 0, and what you get are exactly the equation for the characteristics. Okay, so if you make derivative with respect to x0 of that, you will get x minus x0 divided by time, and then derivative with respect to that would give you the initial velocity, and then it's just the rays that we get. Question for the rays. So this maximum principle allows to select the viscosity solutions. Okay, so that's when we don't know how to select the solution, we have to take this thing. So now, of course, what you see is that it could be, so typically if your psi0 is a smooth function, so you're looking at the max of this thing. So basically, generically, the max is attained only at one point. So if you pick any x like that, there will be only one x0 which will maximize this thing. But then, if you look at places where you have two or more values of x0 which are maximizing this thing, typically it will be a set of codimension 1. Okay, so what does it mean, a set of codimension 1? It means that it's a set of dimension d minus 1. So for instance, in space-time, for the one-dimensional Burgers equation, so space-time is 2D, codimension 1 will be a line. So you have a line in space-time where lines in space-time where the maximum is attained at two values. Okay, so these things are the shocks. So these shocks are places where the maximum is attained at more than one value. Okay. So in dimension 1, it's isolated points, so or lines in space-time. In dimension 2, it's lines. In dimension 3, it's surfaces. Okay. But then you can generalize this thing and look at positions where the infimum is attained at n distinct values. And this is a set of codimension n-1. Okay, and then you have other kind of singular. So you can through this formula you can classify all the singularities that you expect to see in Burgers equation. So depending on how many points at how many locations the supremum is attained, and on whether or not the maximum is degenerate there. Okay, degenerate in the sense that it's not just a parabola, it's a quartic function, for instance. Yes? So it's a singularity of psi. Okay, so you have a field psi of x and t. So at locations where the minimum is attained at two values of x0, basically it corresponds to a discontinuity of the derivative of psi. So psi is losing its smoothness at such points, and its derivative is discontinuous. Okay, and that's why it's a shock in the sense that it's a discontinuity of velocity, which is the derivative of psi. So now. So basically, there was some work done by Arnold and some of his students. So to classify all these possible singularities and their metamorphoses, how they change as a function of time in 1, 2, and 3D. And basically, the classification they propose is what I was telling you, is that you call a singularity A and M, where N is the multiplicity of the maximum, and M is in how many points this maximum is attained. So if you look at dimension 2, so I was telling you that shocks are lines. So these shocks are lines of point A12, so multiplicity 1, 2 maximizers. And then generically you have points with a higher degeneracy, where the maximum is attained for 3 different x0. And these are triple points, which corresponds to 3 shock lines merging together. Okay, and then you have also other kind of singularities, which are called the A3 singularities, where this time it's a termination point of a shock. The maximum here is attained for 1 x0, but the multiplicity of the maximum is 3. Okay. So same in 3D, we can do the same kind of thing in 3D. So now the shocks are surfaces of point A12. What we had as triple points now are triple lines, like the blue things here. So these things are A13, okay? Then you have, when triple lines are meeting together, you have a quadruple point, okay, with 4 different values of x0 at the same position, okay, which is this A14. And then, so you have different things. So like these termination points, now they are lines like that, so lines of A3 points, okay? And if these A3 points are meeting a shock like that, so it's a termination point of a border, of the border of a shock, okay? So this will be a A1, A3 singularity. Okay, so you can classify everything. And why is it interesting? It's interesting because it allows you to understand the distribution of mass for cosmology. Okay. So now, what about the metamorphoses? So all the singularity, they are evolving as a function of time, and they are different, and they can go through different metamorphoses change. Okay, but the fact that we are choosing the limit of vanishing viscosity means that actually we can select only some of these metamorphoses. So just to give you, so the way to select them is that after the metamorphose, the local singular manifold has to be what we call locally contractible. So it has to be homotopic to a point. So basically, it means that you can find a smooth function which map it to a point. Okay, so that's a topological constraints. So for instance, let's take this metamorphoses. So here we have 3 triple points in 2D. Okay, and these 3 triple points, they form a small triangle here, which can disappear, which can vanish, and become just 1 triple point. Okay, so for instance, this metamorphosis, it can occur only from left to right. You cannot create this triangle from just a triple point. And this is the limit of vanishing viscosity, which allows you to select this kind of change in the singular manifold. So same for this one, where you have 2 triple points which are merging together. Basically, you cannot create 2 triple points from nothing. So this one also, when you have a line with an endpoint which is disappearing, so you go from that, it's absorbed, you have only that, then again, you cannot go the other way. And as you see, if you pick this thing, and this thing, each time you have this homotopy to a point. While here, you cannot map this smoothly to something where you have only 1 point. Okay. Then there is also this metamorphosis, which is a kind of flip change. So which this time is reversible in the sense that you have 2 triple points merging. Okay, they merge together, and then this and this line are becoming this and this line. Okay, and in that case, basically you can go both ways. Okay, so that's what things about the metamorphosis. And since we have these ideas of counting codimensions, it's clear that if we have metamorphoses in dimension D, typically they correspond to something which exists at any times in dimension D+1. So for instance, if you go from the one-dimensional space-time, where this time, so remember the lines now in time are shocks. So basically you have shock creation, shock merger, etc. So they correspond to this kind of singularities. And basically they also exist in space this time in dimension 2, but there are some restrictions. So the restrictions are like this: is like A3, you're creating a shock, so the shock has to continue to live after. So time so there is some irreversibility. So time, you cannot have the shock disappear. Shock is created, it's existing. So which means that this A3 point always have to have a shock above for time increasing at time positive. While here, for instance, we can have things which are oriented the other way, of course, because we don't care. Same for the merger. The merger is something which is a metamorphosis, so it has to be homotopic to a point after the metamorphose. While here, I mean, we don't really care about these things. And, yeah, exactly. Yeah, but because since the singularities are just defined generically, they are defined in terms of counting codimensions, stuff like that. So basically, these arguments are applying. So of course, the thing which is the main difference between time and space is coming from this admissibility of the metamorphosis. Okay. So this is what I wanted to say about the singularities, general consideration about singularities. So now let's go back to questions which are closer to Navier-Stokes. So now the first thing, yes.
So like when you had say question, so now in the limit, new going to the previous one, basically new going to zero limit.
Yes.
The previous one, so that your this psi of xt is basically given
this
by
one.
This one. Now you're saying that okay, there. So when there is only single minimum, there is no problem.
Yes.
But when there are multiple of them,
yes.
Let's say you have this x01, x02, or
exactly.
something like that. So your velocity at a given position is determined by several previous initial conditions.
Exactly.
Right?
Exactly. So basically, maybe on this sketch is clearer.
Yeah.
So if you fix a given time, so it could be that at these points, which are on shock lines, basically you have different trajectories which are coming there. Yes.
But where does the discontinuity come from?
So the discontinuity just come from the fact that I will come back to the discontinuity, but the discontinuity come from the fact that if you have different trajectories coming from different points, they have to have different velocities.
Yes.
So which means that these two trajectories are giving two different values of u at this very specific point. Because u is just transported by the flow.
U is just transported because of this in the limit u going to 0.
Exactly.
DXDT is constant.
Yes. Because the trajectories that you build, I mean that you get at a given point here, since they are trajectories, they are solving the Euler-Lagrange equation, so they satisfy that. Okay, because they are minimizers, maximizers. Okay. So now let us go back more to a PD consideration. Yes, Jason. Yes. No, because you can have new shocks appearing. You look at this one, for instance. So okay. So here I have done as if all the shocks were appearing at the same time. So it's just a sketch, but you see that. So for instance, here you create 3 shocks, then you have another one. So here you have 4 of them. Then you have a 5th one appearing. Then you have 2 merging, so you're back with 2, 4, and at the end you have only 2. So you see, you can increase and decrease. Exactly. So if you take an infinite domain with a homogeneous smooth function, then you can estimate how the density of shocks would decrease at very long times. And this will give you some estimate on the decaying properties. But I'm not talking about that. But in principle, you can treat everything explicitly in Burgers equation. So now let me go back to that. So basically, let me write down a weak formulation. Okay, so we know that we expect some discontinuities in the velocity field. So we can write the weak formulation of the Burgers equation. So now I'm taking just a 1D case. So weak formulation means that instead of interpreting the equation for the velocity as a PDE, I interpret it in its weak sense, where I say that I take a test function, and I assume that for all test functions that I choose differentiable and with compact support, so defined only on a given interval in space-time. Basically, the integral, so the product of the, so now I'm putting the operator on the derivative on the test function, and I multiply by u and u squared. So basically, it's as if I had multiplied by phi the equation and integrated it by parts. Okay, so and this is the part which is coming from the initial condition. So now the weak formulation of Burgers is to say that for all phi sufficiently differentiable and with compact support, this is satisfied. Okay, so this is what we call the weak formulation. So now, so what the first thing I want to say is that solutions to this weak problem are non-unique. Okay, so as we expect also for Navier-Stokes, for Euler. So the first thing, so there is a very simple counterexample. Is the following thing: is to take an initial velocity, which is minus u if x is negative, and plus u if x is positive. Okay, so something which looks like this heavy side. Okay, and now basically it's a very simple exercise because you see, I mean, the x dependence is not very complicated to show that if you put this equation in this thing, you have two possible solutions. One which corresponds to maintain this shock for at any later time. Okay, and this will be what we call an expansion shock. And the other one, which will be to have all these points moving to the left, all these points moving, moving to the right, all these points moving to the left, and to have a solution at time t which looks like that, which is something that we call a rarefaction wave. Okay, so these two solutions exist for this initial value problem with this weak formulation. Okay, so now we know that because of having put viscosity to 0, in principle, we should be able to select only one solution. So now, basically, the viscosity solution, we know that we can write it this way. Yes? What? How the left one is? So the expansion shock is just to maintain the same solution as the initial solution at any later time. Okay, so that's, you say that u of x of t is u of 0 at any time. And this will be a solution to the weak problem. So now, let's see a bit better if one of these two solutions is actually violating the constraints that we get from viscosity solutions. So we go back to our maximum principle. So now what we know is that okay, so this I have already said it. So if it's smooth, the supremum is attained everywhere. If there are points where it's attained at several positions, there are shocks. So now let's try to get a geometrical interpretation of this maximum formula. So basically, we have a function psi 0 here, okay? And now what we do is that we look at the supremum of the distance between this psi 0 and a parabola, a given parabola, which is centered on x. So this kind of parabola, which is centered on x, which has a curvature which is increasing with time. I'm sorry, not a curvature, a radius of curvature, a curvature which is decreasing with time. And now, basically, what we have is that if we have a shock, it means that this parabola is touching, for a given x, is touching our curve psi 0 at two different points. Okay, so generically, in any position, the parabola will touch only one at one point, but there are some positions, some locations, some center of the parabola x, where it's touching at two positions. Okay? And this is a shock. This is a place where we have a discontinuity of the velocity because we have both this x0 and this x0, which are entering the shock at this time t. And they enter it at position x. Okay.
Question is psi,
Yes.
the thick line is psi 0 x0. Is it? No, this one is just half.
So this thing here
Is the psi
is
0
psi 0.
psi 0 x0.
Yes, and this parabola is 1 over t x0 minus x squared. Okay, so it's a parabola.
So at these 2 points, psi
Centered
is
on
0.
x.
Psi is 0.
Yes. So at these 2 points, I have different. No, they should touch at the same location. The same. No, it's like this. And psi and psi of x is this height.
But at x
Psi
naught
is-
should be 0. Where is the 0?
So this is x0.
So where is it? The parabola should touch the base, right? At x not equal to x.
So basically, my parabola is centered on x. Okay.
But at
But
x not
at-
equal to x, it should be 0.
No, this point is that thing is 0, right? That psi 0 of x0 is equal to 1 by 2t x0 minus x whole square. Right?
Yeah, but so here I have a parabola with an offset. So if you want, I have put psi of x on the right hand side.
Ah,
Okay, so I'm moving down my parabola until and once it's touching, the place where I stop it is exactly psi of x.
Oh, so it's parabola plus some constant.
Yeah. So if you want, I rewrite this as the sup over x0 of psi 0. And then I put psi inside. Okay, but it's just a geometrical representation. Okay, so which means that, and then it allows you to do some hand-waving construction of the solution in the following way: is that so you have your curve psi 0, you put a parabola without knowing psi of x and t, which is the offset of the parabola. So you put it very large so that it's not touching anything, and then you decrease psi until it's touching the curve. And once it's touching the curve, the height at which you stop it is exactly psi. Okay, and then so typically it's touching at one position. Okay, but for shocks it's touching at 2 different positions. Okay, that's okay. So now these 2 positions are giving you the left particles which is entering the shock and the right particle which is entering the shock. So now the left particle is having a given velocity, which is nothing but minus the slope here. Okay. The right particle is having another velocity which is minus the slope. And you see that because of this, so thanks to this geometrical construction, because the parabola is convex, basically you have to have the slope here smaller than the slope there. So which means minus the slope here larger than minus the slope here. So which means that the velocity on the left of the shock has to be bigger than the velocity on the right. And this is a constraint coming from limit of vanishing viscosity. So which means that when I go back to this thing, here actually I'm violating this constraint because my left velocity is less than my right velocity. So the shock is the wrong way. Which means that this thing is not acceptable. Okay. So the real solution should be this one, the one selected by viscosity going to 0. So now, basically this condition, which is to have a left velocity bigger than the right velocity, is called the lax entropy solution, entropy condition for Burgers equation. So it can be generalized actually to more complicated equations, where instead of taking u squared by 2 in the flux, you can take any convex function of u. So now this condition, which is 1D here, is equivalent to the following condition, which is that's why we call it entropy, also entropy solution, is that now assume that you take an entropy pair, so it's a pair of functionals of U, S of U so being an entropy, and Q of U being called the entropy flux. So basically, for any pair of entropy and entropy flux, you have that this transport of entropy is negative. Okay, so entropy can only decrease. So it's entropy usually is only increasing, but so you can think so. So basically, so the entropy is any functional of U which is convex, and the entropy flux is such that the derivative of the flux with respect to U is U times the derivative of entropy with respect to U. Okay, so Q is determined by S somehow. Okay, which means that so if you make it concave here, you can get an increasing entropy if you prefer. Okay, so basically, this condition is equivalent to choose that in Burgers equation, and this condition is equivalent to take viscosity solutions which are understood at the limit of viscosity going to 0. Okay. So now let's think a bit about entropy conditions in dimension higher than 1. So again, we start with our viscosity solution, but this time I will represent it in a different manner. So what I will do is that I will show here the curve in the psi x plane, which is such that, which is parameterized by this thing, by psi 0 minus 1 over 2 x0 minus x. Okay, so basically I just use now x0 as a parameter on the curve. Okay, so now basically, so for different x0, you have different positions there. And now taking the supremium of this thing means that you're taking only the branch which is the highest one. Okay. So typically, this function here, so if you start at time 0, it will be just the parabola. No, I'm sorry, time 0. Yes, maybe it would be easier to multiply by t. Anyway, so at time 0, it will be just the parabola, and when you add some psi 0, generically what you will create are these kind of folds which are appearing here. Okay, so now our entropy condition is so since you are taking the sup here, it means that you're cutting the smallest branch, and typically what you get is a cusp in psi. But you see the cusp is oriented necessarily downwards. You have a cusp like this and not a cusp like that. And this is equivalent, you see, to say that the slope here has to be smaller than the slope there. And so since the slope is minus the velocity, again, it's giving the relation between u minus and u plus. So now in more than one dimension, so now this in psi xy, for instance, so it's no more a curve, it's a surface, which is parameterized by initial position x0, y0. Again, you're creating the same kind of singularity in your while having time increasing. Again, you have to cut through the sup formula. And again, generically, you have lines along which you have cusps. Okay, and this cusp is necessarily oriented toward psi negative. Okay. And of course, then you have all the additional constraints in higher dimensions, which are coming from the metamorphoses that I was talking about. Okay. So now let's continue our parallels with. So now we know how to construct limit of vanishing viscosity. We know how to select weak solutions while the weak solutions are non-unique. And now let's try to see if there is anything about dissipation, so kinetic energy dissipation and the four-fifth law. You remember the four-fifth law is relating third-order structure function of the velocity to the dissipation, energy dissipation. So here, basically, it's much simpler in 1D, of course. So let's assume again that we have 1D, no forcing, that we are taking homogeneous in space solutions. And basically, this is what I was telling you, how to derive the Karman-Oars equation. So basically, you take this equation computed at x, and you multiply it by u computed at x prime. You take the same equation computed at x prime, and you multiply by u computed at x. You sum, you do some manipulation, you take the average, and at the end, assuming that your far from that dissipation is not very important, that basically that this quantity is not very important.
So average is over initial conditions. Right?
Average here will be over initial conditions. Yes. Then what you get is that something which is not the 4th law, which is the 12th law, okay, which is telling you that the third order structure function, so the third order moment of the velocity difference is proportional to -12 times epsilon. So epsilon is the rate of energy dissipation. I didn't write it here. Yeah, it's the same. It's nu times average of grad u square of dxu square times L. So you see, it's exactly the same structure as in the 3D turbulence with something which is proportional to L. Okay, so starting from that, if you are having this too strong phenomenological view à la Navier-Stokes, à la Kolmogorov, so basically what you will say, okay, so now I have a scaling exponent which should be 1/3. Okay, so now if we look at so yes, but it's not true. So the first thing is to relate. So now there is one way to relate dissipation to shocks. This is the first thing. So in order to relate the dissipation to shocks, basically one can explicitly compute, asymptotically compute using match asymptotics, the dissipation due to any shocks with a finite viscosity. So assume that viscosity is very small. So typically you have a shock which is not a discontinuity, but very thin, but smooth. Okay. So typically there is one way to zoom inside the shock is to assume that the shock has a width which is of the order of the viscosity. So it's centered somewhere at x star. So you define a new variable y, which is the rescaled x inside the shock. So now you can make this kind of perturbative expansion. So you just say that locally the velocity, you can write it as a sum of powers of nu, okay, with different functions. This you can plug it inside Burgers equation. Then you by defining the shock speed, so the speed of the shock, which is the half sum of the velocities, and the shock size, which is the difference between the two velocities. Basically, what you get is that locally the dominant term is behaving this way. Okay, so the profile of velocity is like a hyperbolic tangent. So locally here inside, if you zoom in, you will have something which looks like a hyperbolic tangent on scales of the order of y, and of course with an amplitude which is s. Okay. So now, next step. So now that you know that, you can compute the time derivative of the energy due to this specific solution to get some dissipation. So it's the same as that, okay? And you just write using this form for the velocity. And what you get at the end is that the time derivative of the energy inside the shock is going like minus the cube of the size of the shock divided by 12. Okay, so you can compute everything explicitly. So which means that there is a dissipative anomaly in Burgers. There is dissipation inside the shocks, and the average dissipation is such that basically you're summing this thing. You're doing a sum of all these things over all the different shocks that you have in your solution, and you divide by L in order to have the dissipation to have it per unit space. Okay, so it's 1/12 of S cube. So it's the average of the cubic size of the shock, typical number of shocks divided by the length. So this is like the number density of shocks. So now what you see is that dissipation is going like S cube. Okay. S is the size of the shock. So now having S positive, which means having U minus larger than U plus, so an admissible shock, is equivalent to have a positive dissipation. So if you are putting shock the other way, basically this shock will put energy inside the solution. Okay, they will give energy to the solution. So which is unphysical because we are willing to look at the limit of vanishing viscosity. So, but finite viscosity means that you are dissipating energy. Okay, so having a positive locally at each shock, having a positive value of the dissipation is equivalent to what we call the lax entropy condition, which is to say that U minus is bigger than U plus. So now let's go to structural functions. Continue to do what everything that we can try to guess that we want to understand from Navier-Stokes. So velocity structural function. So remember, it's the piece moment of the velocity difference between 2 points. Okay. So typically, my solution will look like that. So I will have a number of shocks with different sizes at different locations. Let me assume that I take L small, and typically the distribution of my increment will look like that. So I will have the increment will be equal to minus S1 here, with a probability L by L. Okay, so basically, if I look at the probability that a small gap of size L is intersecting my shock, this is like this L divided by capital L, okay? Then it will be minus S2 with the same probability, minus Sn with the same probability. Okay, so this is the fraction of space where the increment, where the x is such that my shock is between x and x plus L. And of course, for all the remaining parts, which is a probability which is almost order 1, the velocity is smooth. I can just Taylor expand my velocity, and I have that the increment is just L times the gradient. Okay, so from that, I'm writing now the structure function. So by doing an average with respect to this distribution. So all, yes.
Shocks are randomly distributed.
Yeah, I assume that shocks are randomly distributed. So now what I get is that I have two contributions. One, which is coming from shocks, where typically for all these guys, the velocity difference is of the order of S. So what I get when I take the piece order, I get S to the power P. Okay. So this minus S to the power P. And this is happening with a probability which is of the order of L by L. Okay. And then this part here is giving another contribution, which is like, now I'm taking the piece power of that, so which is L to the P times piece order moment of the gradient. Okay, so I have two contributions, one which is proportional to L, the other one to L to the P. So now depending on the value of P, so remember L is small, depending on the value of P, one or the other will be dominant. So if P is less than 1, this thing is dominant, is bigger than the other one. If P is bigger than 1, this guy is dominating. So at the end, it means that if I'm looking at my exponent, structure function exponents, basically I have this behavior. So for P less than 1, I have this zeta P equal to P. And for P bigger than 1, it's saturating at 1. Okay, so remember, compare this to what we would have guessed from Conroe of 1941. So we had this Forfeit law, which was telling us, the cube moment, which is 2, 3 is here, is correspond to zeta P equal 1. So the third order moment is here. And then K41, we just say, okay, we just draw a line like that. And you see how wrong it is. Okay. And then, of course, you clearly, with this formula, you clearly recover the 12th law. okay, the equivalent of the 4/5 law, which was telling us that S3 is -12 type epsilon L, because remember that epsilon here is just 1/12 of the dissipation in all shocks. Okay, so you just plug this epsilon here, the 12 are simplifying, and you get this term is exactly this one, for p equals 3. Okay? So now, let me continue, and now let's look at what's happening with forced Burgers equation. So now remember in the first case, so now I'm assuming that my potential, so you see now it's a plus, before it was a minus. It's a mess. But I think this is consistent or not. No, it should be minus here, I'm sorry. So here it should be minus, so that here we get minus. So anyway, so basically take the forced Burgers equation.
The earlier on, are you assuming that the shock density is very low? I mean,
What?
Density of shocks is very low. Are you assuming that in the previous one?
No, I'm
L
assuming it's order 1.
L is still much greater than 1.
So,
right?
so basically density of shock, it depends on time.
Yeah, but I'm saying that this L, curly L, is of course much smaller than capital L, but much greater than 1, right? I mean, we can have multiple shocks within this.
No, this small L, you can send it to 0.
But I thought this L, when you write down this 4/5 law,
yes,
you actually assume that it's much greater than 1, but much smaller than capital
No,
L.
no,
Right?
actually not. The only thing I'm assuming in this thing is that, in order to get that, is that this term is going to 0.
So if I compute that,
When nu is going to 0, in the whatever is L.
so if I take within L, there are n shocks and distributed by some Poisson distribution,
Yes.
they give it the same answer?
Yeah, sure, it will. Yeah, yes. So it will give you the same answer. And actually, with this kind of ideas here, of putting the number of shocks, you can even look at situations which are non-stationary, for which the number of shocks is decreasing as a function of time. So basically, and both the size and the number of shocks are decreasing, the two of them. So basically, typically, if you take time order 1 and the size order 1 and the smooth initial condition, basically this will be order 1 also. So let me turn back. So here, I'm sorry, it should be minus. So so now again, remember you can write down from the velocity, assuming that it's potential. You can write down Hamilton-Jacobi, Hopf-Kohl transformation. Okay, so you are now having this heat equation with a multiplicative noise, with multiplicative forcing, and still you can use the Feynman-Cake formula to integrate it. So now it's a bit more complicated because it's not just the heat equation, so you also have this forcing term. Okay, and you write it this way: is that theta is now the average of this exponential here. So again, I have this 1/2 nu times the initial potential, but this time I have to add before I didn't have this term. Okay, now I have to add the integral of forcing along the path, and now the average here is with respect to again to this Brownian motion. Okay, where typically I'm fixing the final position to be at x.
So why there is not a the x dot square term in the exponential?
No, but it's inside the average.
Ah.
Yeah, so because it's coming from the average with respect to Brownian motion, which is here.
And
okay, so now I can rewrite it this way.
Can I just go?
Yes.
There? And then you don't have to worry about the Jacobian. There's usually also a f prime kind of term, right? Because going from the noise to the forcing.
So I'm assuming that this F is smooth with respect to space.
Even if it is smooth, but it's more than quadratic. See, like the corresponding Lanzweig equation corresponding to this Fokker-Planck equation theta.
Yes.
Would be like dx is equal to this plus the force, right?
It will be like that, no?
So now if I go from this theta to x, there is usually another term coming from the going from distribution of theta to distribution of x, right?
So basically, here they're just differing through the new factor.
Yeah, that's fine. See, the Lanzweig equation, if I just want to write down corresponding to that Fokker-Planck equation, so dx ds equal to this term plus there is a force term.
Yes.
Right. So therefore, eta is this minus the force term.
Yes. No.
No, not forced by something else.
I'm not interpreting this as a Fokker-Planck.
Okay.
Okay, but then I'm just using the Feynman-Cake. So basically, I'm assuming this theta is a quantity that is computed along a path. Yes. And now basically, so this is just some people are calling it also the Poisson equation in the stochastic systems. So basically, this is just the Feynman-Cake representation of this equation. They call it Poisson because usually they don't they look at stationary solutions.
This one doesn't conserve integral of theta, I guess, right? No. This equation doesn't conserve
no. Yes, indeed. So it's not a Fokker-Planck.
That's like a source term.
Yeah, it's a source. So it's exactly the source. So now you write it. So you rewrite this average with respect to nu by putting some path integral. Okay, so indeed you have this 1/2 of x dot square appearing. Okay, and again you see that you have 1/nu everywhere. So again, now you can do a saddle point approximation to get what's happening when nu is going to 0. So you will pick up. So now instead of writing the infimum, I wrote the supremum. I wrote minus infimum because it's mathematicians prefer to do it this way. So now your potential at time t at position x is obtained as minus the infimum of some action minus the initial potential. Okay, and the action is just now it's not just x minus x0 squared. It's the integral of the velocity of this path minus the potential along this path. Okay, so it's really an action. Okay, so now what does it mean? It means that again you start. You want to know the solution at x at time t. Basically, you construct all the paths that are arriving at time t at position x, and for all these paths you compute this action, and you pick the path which has the minimal action. Okay.
F is a random function.
If it's
F is a random function. F is still a random.
F is still random, yes, but I think that here you have to assume that it's smooth with respect to space. I think that it's complicated to put it white noise, but I'm not able to read what was done by Martin Heirer. So maybe that's what he did. I don't know actually. So because if you put white noise in space and time here, it's a KPZ. Okay, so now again, a trajectory which is minimizing this action is satisfying the Euler-Lagrange equations. Okay, but now the Euler-Lagrange equations is a 2-dimensional, 2 times d-dimensional dynamical systems, where the path has a given velocity and the velocity is accelerated by the force. So it's a Hamiltonian system. Okay, it's the system associated to this action. And the velocity is obtained by taking the velocity of this path at time t, and the position of this path should be x in order to get velocity at position x time t. Okay, so basically it's more or less the same as in the unforced case, except that now we have a force. Okay, so there is no. So in the unforced case, the velocity was conserved because simply we had v dot equal to 0. And in the unforced case, since we had v dot equal to 0, we could just write the ballistic thing. So it's exactly the same thing. Okay? There is no new concept actually. Okay, so now from that we can construct a statistically steady state. So how we do it? We just send the initial time to minus infinity. So we are just doing as if we started a very, very long time ago, and we have forgotten the dependence on the initial condition. And so now, this time, so basically in this equation, here we can forget about this psi 0. And now the integral, instead of being from t0 to t, is from minus infinity to t. Okay, so now we are minimizing this action from minus infinity to t. Okay, so basically, at start t, we get some x position, and at each position, there is at least one path, which is going back in time. And this path is such that it's minimizing this action over all possible paths that arrive at time t at this position x. So such a minimizer, which is minimizing up to t, is called a one-sided minimizer. Okay, so it's one-sided in the sense that it's going from t to minus infinity. Okay, so now again, the shocks are positions where the minimizer is not unique, where you have two minimizers. So these are shocks. Okay, so you have more than one minimizer. Again, you can do the same kind of dimension counting in order to construct all the possible singularities that you get in the flow. So there is nothing more than what we saw in the decaying case. But then there is something which is giving more information, is that if now you consider that your spatial domain is compact, so that you're not living on the full line, but for instance on the periodic domain. So all these minimizers are actually converging toward each other backward in time. And this it's just a consequence of the variational principle, of the infimum principle. It's just that if they were not converging, then it will mean that at some point, if you go far enough in time, it might cost less to jump on another trajectory, which will have less action. Okay, so basically, there is no other choice than having all these things converging to each other. So of course, if the domain is compact, it's because jumping to another trajectory has a finite cost. So if the domain is infinite, then maybe there is a trajectory which is very, very far, which has a very, very good potential there. But then the cost of kinetic energy to go there, it would be too large. Okay, so they will not converge to each other. So here, the fact that it's compact means that there is a cost, a finite cost, to jump on any other trajectory, which is given by the domain size. Okay, so by the kinetic energy, you need to move to another trajectory, and this basically, if you go far enough in time, at some point, this cost will be nothing compared to being on another trajectory where the potential is much better. Okay, so this is hand waving, but it's a mathematical proof of that. So now, then, these things, actually, this convergence is more than that. Actually, they don't converge. They are not just converging to each other. Actually, they converge to a specific trajectory. And this specific trajectory is actually a specific minimizer, which is minimizing the action at any time. So it's a kind of global minimum. And it's called double-sided minimizer. And basically, so there is one trajectory. here somewhere, which at any later time will still be a minimizer. This trajectory will never be absorbed by a shock, if you want. Okay, so now this is the sketch. So typically you have all these different minimizers. Among these minimizers, there is a special one, which is this global minimum. Okay. And then in between, in places where you have more than one minimizer, you have shocks. Okay. And all these shocks, basically, if they are situated, you see, in places which are converging toward each other backward in time, they have to have a finite life, the finite age. Okay. But now the thing is that here we are living on a compact domain. So assume, for instance, it's a periodic domain. So actually, what's happening in such a periodic domain is that this point and this point by periodicity. So you take the leftmost point approaching the global minimizer, the rightmost point approaching the global minimizer, and these 2 points by periodicity, they have to be the same points. So which means that there is another shock here at this point, which is the periodic image from the other one. And this shock is a special shock that we call the main shock or the global shock. Okay. So we have this picture. So we have all shocks which are not the global shock have a finite age. Then if you look forward in time, at some point they will merge with the main shock, with the global shock. And then all the minimizers, when you go backward in time, they just all approach to this global minimizer. So the picture of for shocks is the reverse. Okay, so you have the global shock like that. So all shocks have a finite age, and they correspond to different branches, which at some point will merge with the global shock. Okay, it's a kind of dual picture of the minimizers. So now, yes. I'm sorry? Yes. Exactly. The global shock is there is only one. Yes. And shocks cannot split. So a shock will always live in the future. So if you pick at any time, you look at all the shock, there is only one, so which is this one at this time, which has an infinite history. And this, if you go at any later time, it would be the same guy. So now let's try to see how to make this in higher dimensions. So now in higher dimensions, so here basically what we did is that we had this idea of periodicity. So let's take a two-dimensional periodic domain and let me unfold it to the full space. Okay. So this is my periodic domain. I unfold it, so I have a tiling in the two-dimensional space. And now, basically, I have in this domain, I have bunches of trajectory which are converging to a given replica of my periodic replica of my global minimizer. Okay, agree? Basically, in my domain, for instance, the yellow piece here is approaching this guy. The blue pieces here is approaching all the minimizers starting from this blue piece will approach this one. So that at the end, you see, you can define somehow a kind of tiling of the space corresponding to patches of positions from which minimizers are approaching a given replica of your global minimizer. Okay, so now you just use Euler formula. So in 2D, there are a lot of topological constraints. So you use Euler formula, which is telling you that if you have a tiling, so basically you have that the number of vertices minus the number of edge plus the number of vertices, edge, and the number of tiles, of course, is equal to 1. So you have this constraint in 2D. So that from that, and assuming that generically, if you have connections between lines, they are triple points. Generically, they are not quadruple points, but triple points. So which means that the number of edge and vertices are related together. So at the end, what you have is you necessarily have an hexagonal tailing. Okay, so and this is what you see here. So it's hexagonal in the sense that you have 1, 2, 3, 4, 5, 6 pieces of shock surrounding the tailing, with 1, 2, 3, 4, 5, 6 triple points. Okay, and so now if you refold it to the torus, to the two-dimensional domain, actually it corresponds to having this thing. So on the torus, so you have 2 triple points, which are connected by 3 shock lines. One going around the 3 possible rotation and around the torus. And so basically, this hexagonal tailing is defining the main shock. The main shock in 2D has this shape. In 3D, there are less topological constraints. And for instance, this is one possible tailing, so it's a bit more complicated. So you have triple points everywhere, but you have pieces which are hexagons and other pieces which are squares. Okay. So now to finish, I just want now to explain you a bit more about the way to construct the solutions, at least in 1D. Yes. Something which go, yeah, it can go twice around the torus. Yes, of course it can. So basically, it will make this hexagon, for instance, having a distorted thing in somewhere, but it's possible. It's even generic to observe it. So now, so let's go back to 1D. So now in 1D, so basically, remember there is this global minimizer toward which all the minimizers are converging backward in time. So it happens that this global minimizer is a hyperbolic trajectory of the Euler-Lagrange equation. So hyperbolic trajectory means that it's a point which has a stable manifold and an unstable manifold. So it has 2 eigenvalues, which are plus lambda minus lambda. Okay. So now, as it's a hyperbolic trajectory, it means that if you look at all the trajectories which are approaching it backward in time, they are all sitting on the unstable manifold, because this is the definition of the unstable manifold. And so since they are on the unstable manifold, then you can use the properties of this unstable manifold in order to characterize the velocity field. Because, so you see it, so if you plot it in position velocity, so you have your global minimizer at a given time is here. So typically, your unstable manifold has a given shape like that, and smooth pieces of the solution are pieces of this unstable manifold. So, for instance, they are regularity results on the unstable manifold. So, if the forcing is smooth enough, then the unstable manifold is smooth. So, which means that this allows you to characterize regularity property of the solutions outside of shocks. Okay, so which are directly resulting from the regularity of the forcing. And now shocks, how they are here. So shocks are corresponding to places where you have loops, local loops in the unstable manifold. And remember, so a shock is a place where you have a cusp in the potential. So the potential is continuous. Okay, so the potential is nothing but the integral of the curve here. So which means that the place where you have a shock is determined by applying a Maxwell rule, by requiring that the 2 areas that you cut in the loops are equal. Okay, so this is just a consequence of the continuity of the potential. So I mean, this is typically how the solution can be constructed. And now the main shock. So the main shock, you see, so we are living. So this is the periodic domain. So the manifold is doing something like that. Then it's folding around the torus. Okay, so it's folding around the torus, which means that it's reappearing here. And same the other way, so it's reappearing there. And of course, it can never self-intersect itself because it's a invariant manifold. So now that you know that, so basically the main shock then, which is, it corresponds to a jump between these two branches of the unstable manifold. And this jump, where do you put it? Simply you put it at the place where the mean area below the curve is equal to the mean velocity that you have fixed, which is conserved by the dynamics. So the mean velocity, average velocity is conserved by the dynamics. You have put it to 0. So then the main shock is such that the area below the curve is equal to 0. Okay. So that's the end of what I wanted to tell you on burgers. Questions?
Will you write down some references like this or also the previous lectures?
Yeah. So I have put some on the on the website, but I can give more actually. If I can just summarize a bit what Burgers is telling us. So Burgers is telling us how to understand non-uniqueness of weak solutions, how to relate this non-uniqueness to energy dissipation, how to select solutions both from an entropic level and geometrical level at the level of velocity field and as a viscosity principle and variational principle, okay, and then Burgers is telling us how to relate the singularities, namely the shocks, to some statistical quantities such as the structure functions, okay, and Burgers is telling us how to construct a statistical steady state and how to construct the solutions in terms of some Lagrangian dynamics, which are given by these Lagrange equations. And basically, these are the different questions which are still completely open for Navier-Stokes. Okay.
So one question was, I mean, so when you do like when you're driving the system, I mean, finally, let's say you're looking at this that spectral thing. I mean, what is it called? The scaling, the multifractal plot. So here, what do you get? I mean, with the driving, you still.
So with driving, you will get the same thing simply because at a given time in the steady state, basically, generically, the solution looks exactly like in the decaying case at time 1.
Okay, so in some sense, the steady state is independent of how you get it. So that's why you.
Yes. So the only thing you need is to have a smooth forcing that you need to force at large scales. If you start to force at small scales.
Okay. So
for instance, assume that you take a spectrum of forcing, which is a power law. Okay. In that case, basically, you might create. So basically, this curve will become Roth. Okay, and basically you can create many shocks in many places. So you can have a number of shocks which is dense, and this is the case for not only for KPZ, but also for other systems where you put just a power law forcing in Burgers.
But in KPZ, there's no power law, right? It's uncorrelated.
Yeah, so it's a flat power law if you want.
Oh, you need.
Yeah. Yes. So basically here everything is under control as long as the forcing is, I think it has to be twice differentiable. It has to be twice differentiable, otherwise there is no real notion, not the forcing, the forcing potential. Sorry, mistake. So the force has to be differentiable, or the forcing potential has to be twice differentiable. So because at the end, you see you're constructing your solution thanks to this dynamical system. So you are constructing the unstable manifold of a specific trajectory of this dynamical system, and this is how you construct your solution. And in order to have an unstable manifold, you have to have this force differentiable. Otherwise, it makes no sense to construct this manifold.
But so if you're doing KPZ driving, then how does this function look like? This CP as a function of P, the fractal dimension?
So there was a question. So in KPZ, the velocity is ill-defined. KPZ, okay. your potential is white noise.
Okay.
So the gradient of potential.
Okay, so it's
so velocity.
Moments are not even.
Yeah, I think that moments are not even defined. I think there was a question in the chat.
Yeah. So the question is. So it says, you said that with rough forcing, you can have space filling shocks. Does that change the singularity spectrum?
Does this change the?
You said that with rough forcing, you can have space filling shocks. Does that change the singularity spectrum?
Yeah, sure. This will change the singularity spectrum because now so if you have many shocks like that, it could be that the shocks have a size distribution which is not just order one. So basically, in everything that I explained here is basically I was assuming that all the S all the shock sizes were of the same order with a simple distribution. But now you can imagine that the probability to see a shock of a given size is itself a function of L. See that over L you have so as if you had a multifractal distribution of shocks, of shock sizes. And then this will change completely the singularity spectrum, of course, and can lead to different behavior of the scaling exponents. But this is unsettled. Thank you, Jan.